So this is the presentation, Alexa, Who's at the Door? I'm Dave Olarte. I'm part of the Medical Informatics Institute at Cerner. I have a background in real-time systems, foreign system interfaces, and my work at the Medical Informatics Institute. So why did I do this in the first place, this Alexa thing? These two boys are the reason why. I have two teenage, I'm sorry, that's not going to work either. I'm getting over a cold, so I'm sorry if I cough and annoy you. I have two teenage boys, Jeffrey and Philip. They're my youngest, and they are the most spoiled. They're very independent, and they hate, you probably heard this, they hate the idea of being monitored. They say, I should be able to come and go as I please. Wait, let me say that right. I should be able to come and go as I please. I hear that all the time. And we say, we should know where you're going, who you'll be with, and when you'll be home. Pardon? So the sticking point is when you'll be home, because if they're out past curfew, it costs them $20 on the spot. So they have become experts at quietly sneaking in the house. I have a driveway alarm mounted in a tree by the driveway, and it just beeps when a car drives in. And I figured out that it's easy to just reposition that alarm so that it doesn't ring when they come home, so we don't get a beeping in the house. So it seems to get knocked out of position a lot. So my idea was, I have this Raspberry Pi, a door cam. They can't reposition the door, or can they? So the ultimate goal of my project was to have Alexa tell me who's been at my front door the most recently. That's simple. The goal of this talk, the reason why I'm giving it, is for you to walk out of here and say, I didn't know this stuff was that easy, because when I got done with this project, I was amazed at how easy this stuff was to do. So I'm going to go against the suggestions that have been made and demo the very first thing. So this is an Alexa tap. Ask, who is at the front door?
I predict that no one is at the door with 100% confidence.
Can you guys hear that in the back? Okay. It's up as loud as it'll go, and there's no sound out on it. All right, so I have a Raspberry Pi, and I keep the cover on the camera because I don't want it to start recognizing other stuff and screw up my presentation. So Raspberry Pi in a plastic case with a camera sticking on the outside of it. So I'm just going to, the lighting here is bad, so it may take a little while to actually pick up a face, but I'm just pointing the camera at my face, as though it was on the door and I was walking up to the door. And I'm waiting way too long. It should have just taken a second. And my hands are shaking because I'm nervous that it didn't work. Ask, who is at the front door?
I predict that Hulk is at the door with 37% confidence.
It didn't work. And it's mostly because the lighting's bad. We actually trained it for several images besides mine. It should have said Dave is at the front door. But the confidence level was really low. That's my only out on that one. So the camera's covered again. All right, so demo failed. That was great. At any rate, awesome, yeah. So what just happened? There were three parts to this. There was the Raspberry Pi hardware. There was Alexa and the little bit of Amazon code behind that. And then there was the real creamy filling, which is face recognition. So I'm going to cover the first two first. Raspberry Pi. So this is, I don't need to hold up the Pi now. This is an exact picture of what I just held up. It's a Pi single board with a camera on a ribbon cable coming out of it. The camera is part of the Pi package that I bought. It all came in a nice little kit box. Simple, $35. My original thought was we have a attached garage and a door, inside door that leads into the kitchen. So I was going to drill a hole in the door, install one of those peepholes, and then stick this Raspberry Pi on the inside with the camera stuck to the peephole lens so it would look through the door out. And also it would detect when there's no image so that if they taped over the peephole, I'd know. However, somebody else who lived in the house nixed me drilling a hole in the door to do this project. So that hasn't happened yet. Okay, so the Pi, you can read the stuff. It's just a little single board computer. It's got a video port and USB ports so that you can add a monitor, keyboard, and mouse, and it's just a plain old computer. So this is what the PiCam software does. Captures frames off of the attached camera, looks for a face in that frame, and if there's a face, it uploads it to a web service that I wrote. Because the Pi does everything behind the scenes, you didn't really see it do anything. I have a couple of visual demos to show what's happening. The first demo, to show how simple just reading the camera is, this is the actual Python code, which is 6 lines of code. So it sort of turns the Pi camera into a webcam. Pretty simple stuff. And now I need the Pi to display up here. I'm going to do the switch twice. It's a little awkward. So I have to grab my keyboard, just the standard Cerner wireless keyboard and mouse. And then I awkwardly have to look up to see what I'm doing. So I have to type like I've seen some of you guys type like this. So it's already running a demo. So I'll kill it. These are shell scripts that have a Python command inside them. So the first demo, for the code I just showed you, is just turning it into a webcam, I think. So it's upside down, sorry, just a dumb camera. This cable's massive. All right, so can you switch me back, or would you? So the second Pi demo is finding faces in those frames that it was displaying. So the code that I had on the previous screen, plus another 5 lines of code to locate a face and draw a rectangle around it. 10 lines of code. Other than some imports at the top and some cleanup at the bottom, this is the code. Can you switch me back? Oh, this is really awkward. Naturally, I look up to see if it crashes or something. That'd be awkward. Okay, so a face. So the camera's still working. Now, first time I've been in front of a crowd, still upside down, sorry. This is hard. All right, well, I don't know, but is it upside? It's still upside down. That's why I brought these pictures. My son, Philip, one of the 2 scoundrels that rearranges the camera. The lighting is bad in here for this, and the cable's bad, and this wasn't supposed to take so long. That was supposed to. I wonder if it works better with more light. So just finding a face in every frame it grabs and outlining the face. So that's 2 steps on what the Pi does. Don't change yet. Would you switch now back to the Mac? Okay, so the last thing the Pi does is just to upload it the same way you'd upload an image to Google Photos or Facebook or whatever. Takes the image, puts it in a form, and uploads it, does a post. So from now on, so I don't have to do the switching back and forth, the demos of how it functions, I'm going to run, since Python and the OpenCV software library that I use run on the Pi, on the Mac, on Windows, and they work the same, I'm just going to start using the Mac now instead of switching back to the Pi. Okay, so Alexa. Alexa comes in 3 flavors. The Echo, which is to your left, to my left, is always listening, externally powered. The Tap, the furthest to the right, is always listening, externally powered, but it's low fidelity. And then the Tap in the middle is what I'm holding, and it is not always listening. You have to press a button, which is really good for a demonstration like this where you guys shout out commands at awkward times. So I have to press a button, and it's battery powered, which is really great. So you can take it around with you and play Spotify. So I'm demoing on a Tap. So now we're talking about how I interfaced the Alexa hardware. So the Alexa hardware and software come with built-in defaults, time sports jokes. So, for example, tell me a political joke.
Where does the president of all princesses live? In the Snow White House.
Okay. They're not necessarily funny jokes, but there are also skills that third parties can build and put into the Alexa store. Some of them are like Word of the Day and On Board. I haven't found any useful third-party apps yet. And then there are custom skills, which is what I did. You have to fill in a few forms and then actually do some web service programming away from Amazon to do the work of that skill. So let's add a new skill called Who is at My Snarky Door? This is where you go, but I don't want to depend on being able to hit that URL and all that, so I'll show you screenshots of what it takes. It's very simple to develop the Amazon side of the skill. First off, you have to define that it's a custom skill and a name for it. The name's not really important. It's just for you to identify. And then finally, the invocation name, and that is the words you speak to get the hardware to start working on your skill. So, for example, who is at my door is what I'll say, my snarky door, to activate this custom skill. I create an intent, and an intent is really just the name that's passed between the Amazon skill service and my web service. It's an identifier. So it's important, but it's not important what you name it. It's just important that you remember what you name it. Finally, well, not finally, you have to define some utterances. In the case of my skill, I don't need utterances, but Amazon requires you to enter utterances no matter what. These are things that in a back and forth conversation between an Alexa device, you'd use some of these to respond to the Alexa asking you a question. But once again, they're not necessary, so I just threw some stuff in there. Okay, this is important. You can either pick Amazon Lambda, which is sort of running scripts in the cloud, Python scripts, JavaScripts, whatever. Or you can specify your own web service as what the Alexa skills service actually sends the JSON that it's formed out of your spoken command. It's got to do something with it. So I provided my own web service, and down at the bottom I provided a URL of a web server that I developed and that we'll cover in a little bit. Very simple to do. So, and finally, once you've defined those pages, there's a test page, which is really convenient. You can, it's not highlighted, but you can enter your utterance. And once again, for my skill, there's no utterance. It's just the words to start the skill, and then it does all the work. So it'll form a request and show you the request that it's going to send to your remote service, the one that my custom service. It'll show the reply that service sent, and it also lets you listen to the reply in Alexa fashion. So I'm going to demonstrate only the very last thing, which is to test this web service. I can enter anything. And I'm actually testing my front door service, not the one that I just mocked up for you. Okay, so I can see the request that got sent out. I can see the response that came back, and then I can listen to that response.
I predict that Hulk is at the door with 42% confidence.
Yeah, still wrong. Okay, so now there's the web service that you have to build to actually do the Alexa stuff. I like Python. There happens to be a microservice called Flask that will stand up a web server in just a few lines of code. So specifically, to handle the intent, who is at the door, I created this in, 6 lines of code? First off, it's a function, who is at the door. I access 2 globals, latest face and confidence. I know this isn't a coding session, but those are just variables that are defined somewhere else in my web service. And based on latest face, which is just the text name of a face, like Hulk or what should be Dave, and a confidence level, how sure the face recognition software was that this was indeed the face. And then the last 2 lines are involved in formatting it back into a JSON reply that the Alexa Skills Service understands. So the first line, highlighted, is interesting because it sets up this particular web service request to understand and parse out the JSON that the Alexa skill sent to this service. Otherwise, I have to do a lot of JSON parsing myself. So it made it really easy. It's an add-on to Flask, free, open source. So 6 or 7 lines of code to actually do who is at my door, at least the Alexa part of it. That's pretty cool. There's no reason to demonstrate because it's still going to tell you who's, it's still going to tell you wrong. Okay, so that's it for the Alexa side of stuff. And now for the cream in between. You have to watch this. This is a desperate, desperate attempt for laughs. I don't even know why I put it in there. I think I Googled cloud, and this showed up. So all right. So I got my laughs. That was pathetic. You guys can write that down.
You are being watched. The government has a secret system, a machine that spies on you every hour of every day.
This is from a TV show series called Person of Interest. It's now done. I think it ran for 5 seasons. When I first saw this, it nailed it for me. This is so cool. Video capture, face recognition, face detection, object detection, because some of the other clips show it tracking planes in the sky, and that's so cool, and it's so hard, but I'm here to show you that it's not as hard as you think it is. So, face recognition, it's something that we all do, and I don't think any of us really think about, how do I know that this is my coworker out in the crowd? So, the way they say that we do it is you, the human, pick out characteristics that you've been trained are important. I don't know what those are. Mine are a little different. And then you associate a label or a name with those characteristics. So you're not really taking a picture of the face. You're taking a picture of the characteristics of the face that are important to you, and then you memorize it. And so how do computers do it? Pretty much the same way. However, I left off one thing, physical characteristics. Computers pick out characteristics of images, but they're not necessarily physical characteristics. Associate a name or label with those characteristics and then memorize those. Sort of the same thing. So, characteristics. Some people think, watching CSI, the characteristics that they use to recognize a face are the distance between landmarks on your face, for example, which is really cool. This is a nifty demo. This is a clip from CSI, so I didn't do this, of course. Some people think it's the whole picture, the pixels, everything on it is really important. And it turns out that there are better ways to do it than that. We're using an algorithm that Carnegie Mellon developed called NN4 small 1, which should mean a lot to you. It's a trained neural network which extracts just 128 characteristics or features from a facial image. Not pixels, but characteristics. And I'll talk about that more in a little bit. Compare that to using just pixels, 128 characteristics versus, even if you have a fingernail-sized image, 96 by 96 pixels, that's over 9,000 features, a lot of which are useless, like the background in this image. That's worthless for face identification. So that's really a lot of noise in the process of trying to identify a face. Why would you pay attention to the background? So CMU calls these algorithmically generated characteristics embeddings. You could call them characteristics. The terminology gets really confusing, but so when I say embeddings, it's things that the algorithm extracted that it thought were important in this image. So why are these better than using all the pixels, for example? Well, one important point is that the embeddings, which are the result of mathematical equations performed on this image, they're supposed to be totally unrelated to each other. So each of those 128 measurements, if you change it, shouldn't directly correlate to any one of the other measurements. Whereas the pixels, for example, on the bright part of the cheek, I hope I'm pointing to that, the pixels right next to each other are related. If you have a bright cheek pixel, right next to it is likely to be another bright cheek pixel. So we have fewer characteristics using these embeddings, and they're unrelated so that we can count on the fact that when two of them move, I'm cluttering this up now. So embeddings are better because they're unrelated measurements or characteristics. So we gather, when we train the algorithm that we're going to use, we use a ton of test images, maybe 10 for each person. Each person has a label or a name. So we generate an embedding for each picture of each person, and we pair that with their name or label to create a set. So one set for each test image. There may be several sets with the same label, like Dave. And then we input all of these sets into a simple classifier. In this case, it's a supervised learning model called a support vector machine, specifically a linear support vector machine. Some detail is this is part of a scikit-learn library, which is often used in Python for scientific stuff. So these are used to input to the train method of this classifier, and the output of the train method is a trained classifier object, Python object in this case. So since this is Python, we save this trained classifier object as a pickle file. A parallel in Java might be a serialized Java object that you write to disk. So we can use this trained classifier later to then determine labels of unlabeled embeddings. For example, this is a news source image that wasn't included in the training, and I never associated a name with it. It's just a picture. So I can put this into the embedding generating algorithm, and it spits out 128 measurements, which I can then pump into the classifier that I just trained with all those faces, and it will generate a label and a confidence level. So that is the process of face recognition. Oops. Rats. Sorry. Okay, so I have some demos now. I thought I got all this. These are quick demos. 10:45. Quick demos. Now, they're going to use a camera that's on my Mac, and the lighting is terrible, so it might be hard to see these. But the first one is a demo to show the landmarks on a face, the significant parts, eyes, nose, mouth. O5C and D. Okay, so I have to trust that is it showing a face with because if I turn away, it's not going to see a face anymore. Actually, maybe I can do this without breaking my... I didn't practice this up here. Okay, so it's a little shaky. It's not supposed to show blurry. At any rate, so it's an example of being able to, from a face image, show landmarks. That's an example of the landmarks, and now I can't get my cursor. There we go. Okay, and then this is the process of preparing this image for use in face recognition. So then there's crop align. 5A and 5B. This is all Python. These are demos that were written by me with not much code. Okay. Okay. Does it show my face? I should be able to, this is really weird, turn, reposition slightly, and my eyes should stay on the same level. Do you see that? I did not plan for not being able to see it. Usually I can turn around and, okay. So that's it used those facial landmarks from the previous demo to align the eyes and kind of stretch the face so it's a standard face. Okay, now recognize. Oh my gosh, this will be interesting. 6A, 6B. Okay, this is the whole thing, classifying an unlabeled image. This is exactly what the AWS service, the Amazon Web Service that I wrote did. Okay, oh my gosh. Oh man, this is so weird. Okay, so it should be labeling. You should see a label show up that says, I think Dave is at the door. Now let's put my son Philip, one of the scoundrels, in front. It should have changed to Philip, did it? The label? Okay. Try another one. This is an untrained image. Actually, all the images I'm using haven't been trained. Jerk. All right. Wide-angle cameras, stupid stuff. Okay, so, okay, you get the idea. So that's exactly what the web service does, and it really just returns the label with some text around it that I put in to make it sensible when it shows up in Alexa. And I'm not sure how much time. 11 o'clock. Okay. And finally, I threw this one in to kind of describe what the embeddings were a little better. It's called, I did not write this demo. This is straight out of the OpenFace example stuff. So what this does is identify a face, and it has a globe. Okay, so it's using 3 embeddings instead of 128. And 3 embeddings isn't going to be a very good way to identify a face, but it's just the idea of it. And it's going to draw a dot on the sphere that you see that describes where it thinks my face is in relation to other faces. So is there a green dot? You should see a sphere with, oh gosh, this is so hard. My face disappeared. So the idea is, I should be able to show, do you see 2 faces now? Do you see 2 dots? Okay, the idea is with 3 variables or features or characteristics, the closeness of those 2 dots on the sphere is how close these 2 faces are. I'm going to try one more thing. And this is a good time to remember or to mention, we're all part of the same family, these pictures that I'm using, so the faces, accordingly, are pretty close together. Okay, so 3 faces, lighting, 3 dots. They're still not very close together because we're only using 3 data points. And I think this should be a good example of, did it see Hulk's face? One of the interesting things about the face detection, why are you laughing? Okay. Right. That's what I was hoping to show, is that with only 3 data points, that's a really lousy way to detect a face, is using, that'd be like saying 3 pixels on the display. Oh my gosh, that's no way to do it. And also, this Hulk picture, it turns out through experimenting, it's not really a very good human face either. So it has a hard time even detecting this thing. All right. So, there and back again. Let's ask Alexa. Ask, who is at the back door? Not sure why the long delay is going on. You're ruining my demo. Ask, who is at the back door?
Hulk says Hulk smash.
So, just to summarize, what happened was Alexa, when prompted, took the spoken word, translated it to text, then translated it to JSON, and sent it to my web service. My web service just returned a label, whatever it had cached in there. My web service was constantly behind the scenes updating, or it's supposed to, who it sees in that face cam. I've got it turned off or covered up right now. Okay, that's it for the demos. I have other ones, but time-wise and all that. So leave feedback through the guidebook app. Please leave this feedback. Okay, I'm kidding. We really appreciate feedback, though. I did a talk a couple of years ago, and it was really helpful. Some of it was hurtful, but most of it was helpful. Leave feedback. That'd be excellent. That wasn't, shoot. Questions. We have a few minutes for questions. I'd be happy to answer them. They asked if you're going to ask a question, go to the mic so it shows up on the recording, or you can come up and ask it. That's it. Thanks for coming.